Is it okay if during the presentation I stop my video, or should I keep it on? Because my presentation will be on the screen, right?
It reference both.
Sorry?
Okay.
Your presentation and your camera.
Okay.
Okay. Good morning, everybody, and special to attenders to this event, and especially in this plenary conference. Initially, this plenary conference should be given by the Professor Chauvel, Gerardo Chauvel, Professor in Epidemiology and Population Health Sciences in the School of Public Health in Georgia University State. He is also conducing minority programs like Professor Carlos Castillo Chavez, his college. Both were born in Mexico. In particular, Professor Chauvel is a proud descendant from the Mexico hero in the independence war ago more 2 centuries. This time, his student, Anna Terik, impart this plenary conference. Anna Tarik is a doctoral candidate and graduate research assistant in the Department of Population Health Sciences and at Georgia State University, a School of Public Health. She is second century initiative fellow under Big Data cluster. Prior to embarking to doctoral journey, Amna completed a bachelor dental surgery in Pakistan in 2013 and a master in public health in Georgia State University, USA in 2017. Interesting perfect. He is interested in her research interests include computational and mathematics modeling of the emerging and reemerging infectious diseases, quantitative data analysis, and math epidemiology. It is a pleasure to present to Anna and give you the word.
Thank you. Should I share? Okay. I'm gonna share my screen. Can you see my presentation?
Yes.
Okay. Hello. Hi, guys. I'm Amna Tariq. I'm a PhD candidate at Georgia State University at the Department of Population Health Sciences, and I work with Dr. Gerardo Chauvel that Dr. Jesus just told you about. I'm more than happy to be here on behalf of our lab to be talking about some of the COVID-19 work that we have been doing so far since the pandemic started. And I'll be talking about some of the models that we have been applying to predict the COVID-19 trajectory in different parts of the world and what our predictions have been like so far. So The COVID-19 apparently has been the major catastrophic event of the 21st century, and it has resulted in global socioeconomic and political consequences. The virus's novelty and complex transmission dynamics have resulted in non-pharmaceutical interventions being one of the primary weapons to fight the COVID-19 pandemic, and some of those interventions include the wearing of the face masks, the social distancing mandates, and intermittent and complete lockdowns in different parts of the world, in different cities of the country at different periods of time. And as we know, that new variants of SARS-CoV-2 have been emerging very, very frequently. And recently, the Delta variant is spreading across the world. And we're again kind of seeing resurgences of COVID-19 in different parts of the world. So as the vaccination continues, new variants continue to emerge, we are unclear about the COVID-19 pandemic, that how it might unfold. And because of that, we have been observing substantial morbidity and mortality burden from COVID-19 across different parts of the world. So as we know that as the pandemic or an epidemic progresses, we usually observe aggregated or cumulative incidence data in different parts of the world. We can look at the data for mortality or for the case incidence. As more and more the disease spreads, we get more data. We can build different transmission trees, and we can see how the disease spreads from one person to another. And with the spread of the disease, we also observed different growth patterns in the disease, which could be exponential very early on in the time of the epidemic, or which could be sub-exponential or polynomial, depending on what part of the pandemic or epidemic we're looking at. So as the aggregated or observed incidence curve is or can be seen as in the figure right here, we know that there is multiple different sub-epidemics or multiple different epidemic waves that are combining together or that are being accumulated together to form this one curve. And currently, most of the models that we observe are unable to get to the level of those different sub-epidemics. But it's very important that we do understand how the different simpler or smaller epidemic waves combine together to make the coarse scale epidemic curve. So, like I said, we observe different growth patterns. In case of this figure, we observe that we have epidemics with size. However, we see different epidemic growth scaling in each of these epidemics. And the early epidemic growth usually differs a lot from the epidemic growth that occurs later on in the epidemic, as we observe more exponential growth during the early phase when the interventions are not yet implemented, compared to when interventions are implemented, which could include the face masking mandates or implementing the social distancing, or for that matter, doing the intermittent lockdowns to avoid people from contacting each other. Some of the features of epidemic growth patterns, especially during the first few disease generations, could help improve the understanding of the transmission dynamics of diseases and help us inform the design of models for the disease spread. Importantly, some of the model ingredients, which include the realistic population structures and the modes of transmission of the disease, the different changes in behavior that people exhibit, different spatial structures of the diseases, or heterogeneities in the susceptibility and infectivity of the population, help us understand how the epidemic grows, or how can we scale the epidemic. So, for instance, the initial or early phase of the HIV/AIDS epidemic in the United States was polynomial growth, and it was mostly due to the strong biased mixing of the population, where there were prefer like, or where there was the homosexual behavior across the region. And we do know that this is not a disease like COVID-19, which is airborne. It's spread through bodily contact. And past researchers have identified that the polynomial epidemic growth patterns for HIV were more significant compared to any other growth patterns. And it has been well documented that the cumulative AIDS cases in the United States in the 1980s followed a polynomial growth rather than an exponential growth. Similarly, for the 2014 Ebola epidemic that happened in Guinea, we observed multiple sub-exponential growth patterns, and we could see that in different regions across the West Africa or in Guinea, we observed that there were no exponential solutions when the models were fit to the data. And hence, we need to have models that could account for the changes and admit the non-exponential solutions to the data. And again, like the HIV/AIDS epidemic that happened in the United States, this was also not an airborne disease, and this was also a very good reminder of the USA epidemic of AIDS, or it was a reminiscent of that disease. And again, the prior work on the Ebola epidemic in Guinea also showed that seemingly exponential pattern of the disease was actually at the national level was in fact more of a composition of the local asynchronous and sub-exponential outbreaks rather than having a exponential solution to the data. So to observe the exponential or sub-exponential solutions of the data, we usually look at a parameter or a factor which is called P, which is known as the deceleration of growth or scaling of growth parameter. And in one of the studies, we observed that about 20 outbreaks, all of them exhibited some kind of an exponential growth pattern. And all of these are viral pathogens, and the deceleration of growth parameter was between 0 and 1. So 1 means that the pandemic or epidemic would display an exponential pattern, but as you can see in all of these, the bars, which is the 95% confidence interval, and the little x is the mean, we observe some kind of a sub-exponential pattern. And for instance, for the measles epidemic and the HIV/AIDS, we observe a 0.5 P, which means that it was pretty much showing a linear trend, which is again a category of the sub-exponential growth pattern. So like I said, looking even at the cumulative number of cases, we have the exponential and the sub-exponential patterns. And this is, again, a figure just exhibiting how the different sub-exponential patterns could look like, ranging from being between 0.1 to 0.9. And when a pattern, when the value of parameter P is approximately equal to 0.9, then that means that's almost reaching an exponential growth pattern. So some of the factors that contribute to the epidemic or a pandemic exhibiting the sub-exponential growth dynamics includes spatially constrained networks, population mobility, which could be increased or decreased during the pandemic. Some of the behavior changes, which, for instance, in case of COVID-19 would include wearing the face masks, socially distancing from each other, or intermittent lockdowns or complete lockdowns, then control interventions implemented by the government or the public health people, and then the heterogeneity in the risk of the infection, and then any of the factors, one or all of the factors that I mentioned above. So overall, we need to consider the sub-exponential growth patterns in the design and parameterization of the mathematical models. And past modeling efforts have incorporated different parameters which could, or different mechanisms to account for the growth that is slower than the exponential growth, which includes models that gradually mitigate the transmission rate of the disease, or that include some of the phenomenological parameters to capture the non-homogeneous population mixing, and models which basically can exhibit different spatial network structures. So as the epidemic progresses, there are some epidemics or pandemics that display very simpler structures, and some of them are complex epidemics. For instance, the influenza epidemic in the San Francisco in 1918 was a very simple transmission, would fit a very simple transmission model, such as an SIR type or a logistic type model, because it was a single peak epidemic, and the simple phenomenological model or simple SIR model would fit the data well and provide us with pretty accurate predictions of what might happen in the future, or provide us with good estimates of reduction number. However, some of the epidemics, such as the Ebola epidemic in the DRC that happened in 2018-19, as you can observe, a simpler GLM, or and by GLM I mean the generalized logistic growth model, does not fit well to this epidemic, because if you can see the data, which is the blue circles, it looks like two peaks. And then again, the SARS epidemic 2003 which happened in Singapore, again, the simpler GLM model did not fit well. And the reason is because most of these simpler phenomenological models, one, are single peaks. Second, they show an immediate decline right after reaching the peak or the saturation level. So while this three parameter generalized logistic growth model doesn't fit well, we need models that are able to capture the multiple peaks in the epidemics. And one of the models, the subepidemic wave model, fits well to the multiple peaks in the epidemic. So if you see here, this is again the similar example of SARS-CoV-2 epidemic, and we're fitting the model by performing a parametric bootstrapping approach, which I will explain a little later. But you see that this subepidemic wave model, the top panel, fits well to the data and exhibits the multiple peaks or the two waves, but the GLM model or the GLM fit just fits to that one peak, and it does not look like a good fit, and it shows a near immediate decline. For this SARS epidemic in Singapore in 2003, if you see the figure, the bar graph, it was a two-peak epidemic, which happened because of the two clusters of diseases that occurred at different hospitals or at different spatial scales. So that's why we observed the two peaks, which can then be captured by a model such as the subepidemic wave model. So like we have talked before, the aggregated wave or the aggregated incidence is the only thing that we can observe, but we do not know what happens on the aggregated structure, or how the different subepidemics are combining together to form that aggregated structure. And as the information is disseminated from the transmission tree, it gets lost somewhere between where we observe the aggregated incidence versus where different multiple subepidemics can be observed. And for instance, like I said, the SARS epidemic in Singapore was because of the two hospitals corresponding to the different subepidemic waves, but majority of the models that we were using back then were not able to capture those two peaks, and we were just able to fit that one peak with the model. And hence, using these models, which work well with multiple peaks, helps us identify better the disease process. So some of the dynamic growth models that we use in our study, and most of these, the three of them that I'll show, are the single peak models, and then the subepidemic wave model, which captures the multiple peaks. These models include the generalized growth model, which is a two-parameter model, and this is usually used for the early ascending growth phase. Then we have the generalized logistic growth model, which basically is a three-parameter model, and it is able to capture the peak or the saturation point in the pandemic. Here, the parameter R is usually the growth rate. The parameter P is the scaling of the growth parameter that I talked about earlier, and which basically allows you to incorporate the sub-exponential growth dynamics in the model for the disease. And then the K is the final size of the epidemic, which we are allowed to only observe in the generalized logistic growth model, or while fitting this model to the disease. Then we have the Richards growth model, which is basically, again, a three-parameter model, but this model lacks the scaling of growth parameter, which means that we are not able to observe, or we are not able to capture the early or the sub-exponential growth dynamics using the Richards model. And then we have the subepidemic wave model, which is a beautiful model which is able to capture the multiple peaks, and I'll explain in the upcoming slides how this model works. But this model basically, the building block of this model is a simple generalized logistic growth model that I explained earlier, and then we're using multiple and overlapping subepidemics to make the final subepidemic wave model. And again, in these equations, the DC I dt describes the incidence curve over time. R is again the growth rate. The parameter A in Richards growth model is the scaling parameter, which allows a deviation from the normal S-shaped curve. And then again, K is the final size of the epidemic. In the subepidemic model, the other parameters remain the same. The A sub I is the indicator variable, which basically allows us to identify the C threshold value. And I'll talk about that a little later in the upcoming slides. So like I said, the building block of the subepidemic wave model is a generalized logistic growth model. And we have the growth rate, R, deceleration of growth parameter, and then the final epidemic size. And as you can observe in this figure, where we have simulated some curves using some similar data where we have R, or we have fixed the value of growth rate parameter at 0.3, and then we have fixed the value of our final epidemic size at 100,000, and we observe how the different p-values can be, how the different p-values look, or how the epidemic curves look like at different p-values. So basically, with the overlapping subepidemic wave model, we model each subepidemic, however there are many, with a generalized statistic growth model. And any epidemic wave that comprises of a set of n overlapping subepidemics, and n can mean anywhere from 1 to 5, 10, 20, however many. We model that using a system of coupled differential equations. And here, the equation, which is right in front of you, where C sub I is a cumulative number of infections for the subepidemic I. Ki is the size of the I subepidemic. And like I said, AI is the indicator variable, which is going to be 1 or 0, depending on what's the value of C sub I. So if C sub I is more than the C threshold value, then we have the indicator variable as 1. But if the C sub I value is less, is equals to, is anywhere else than the CI greater than C threshold, then we have it as 0. And as you can see in the figure here, the gray curve shows the aggregated wave. The red curve shows the first subepidemic, and the blue curve shows the second subepidemic, which is taking off as the first subepidemic is declining. And we observe a very little green shade or shadow, which is the third subepidemic, which is again taking off. And if you can appreciate here, each of the subepidemics is kind of declining. So the subepidemic wave model produces an interesting variety of different epidemic wave profiles that I'll show. And we can observe different kinds of subepidemic wave structures as the epidemic progresses. So if we assume that the subsequent subepidemic sizes decline exponentially, then we have this equation where we have the final epidemic size equals to K naught and exponential minus QI minus 1, where K naught is the size of the initial subepidemic. So whatever is the size of the subepidemic 1, that's what K naught will be. And then the total size of the epidemic wave that's composed of any number of overlapping subepidemics can be given by this equation, as you can observe. And here, the factor Q is the interventions or the behavior changes. So any interventions the government implements or any behavior changes showed by the population. And higher the value or the higher the factor Q, the faster the decline in the epidemic size for a particular pandemic. And N, like I explained earlier, is going to be the number of subepidemics from 1 to 5, 10, however many. So given these equations, we can say that the K total, which is the aggregated curve or the final epidemic total size, is equals to N times the K naught. And hence the C total, which is a gray curve, is equals to the summation of all the CIs. And again, C total would represent the cumulative epidemic curve, which is the aggregated curve that we usually observe with any of the data provided by any country, even with COVID-19. We get data from different countries, which is aggregated curve. And then when the number of model parameters is 3, when n, then n equals 1, and 5 whenever n is more than 1. So like I said, there's multiple different epidemic profiles that the subepidemic wave model exhibits. So one of those is the, and this basically allows us to look at the decomposed epidemic wave, which we observe at the larger scale, and we decompose it into multiple incidence curves, which helps us understand the different factors that are shaping a certain shape of the epidemic curve. So this subepidemic model can exhibit an endemic state profile where we have each of the different subepidemics, where each of the different subepidemics takes off about at the same level. Then we have a temporary endemic state where the subepidemic, again, the subepidemics are taking off at a certain point as the first subepidemic finishes, but then they just start to decline at a certain point. Then we have the declining subepidemics where each of the subepidemics grows smaller and smaller in size. Then we have the sustained oscillations where each of the subepidemic has a regular structure and would take off exactly at the same point where the previous subepidemic took off. And then we have the damped oscillation where each of the subepidemics gets damped or smaller as the epidemic progresses. So we can observe any of these profiles when we decompose our aggregated incidence cumulative curve into the different subepidemics. So the N subepidemic wave models, each of the subepidemic, like I said, is modeled by the generalized logistic growth model, which is explained here. So another methodology that we are employing is creating of the ensemble models. And the ensemble models is basically, we are using different models to create one specific model, which would explain best how the epidemic, how the model should fit the data. And for using this, we basically perform a method of bootstrapping, which I will explain a little later. But for instance, if we have ft theta or ft phi, which can denote the set of estimated parameters, then we basically estimate the mean incidence score for the ith model. And then based on the quality of the model fit, which can be measured by the mean squared error or the mean absolute error, or AIC, which is the high key information criteria to select the best model, we compute the weights for each of the ith model. And then we perform a parametric bootstrapping approach where we refit each of the models to the data. We calculate the weights, get the estimates for them, and then we generate an ensemble model forecast. And doing this multiple times, which could be 200 or 300 times, we can construct the 95% confidence intervals and the 95% prediction intervals, and we can look at the 95% confidence interval as to how our forecasts look like. So we use a nonlinear least square fitting of the model solution to the simulated data to perform the parametric bootstrapping approach, where we perform the best fit to the data, which is ft sub I and phi, comma phi, which is the set of the model parameters. In this process, there is two sources of parameter uncertainty. One is the noise in the data, and then there's assumptions built in the model. So ignoring the noise in the data can result in misleading inferences and incorrect information to the public health professionals to implement the policies. Therefore, we need to incorporate the noise in the data, and we could use a Poisson error structure or a negative binomial error structure to perform that. And here, the best fit to the data is the any fit, which has the smallest distance between the data set or the data points and the model, and where the t sub I, say phi hat, is basically the set of model parameters that minimizes the sum of squared differences between the data and the corresponding model solution. So like I mentioned earlier while talking, that we perform a parametric bootstrapping method to quantify the parameter uncertainty in the model. And here we basically start with the time series data and we obtain the best model fit. And then from the best model fit, we simulate 200, 300, 500, whatever's your number of bootstraps. So we simulate the number of bootstrap realizations for the incidence curve, and we incorporate the noise or the error structure, which could be which usually is a Poisson structure, but depending on the variance in the data, we would incorporate the negative binomial error structure as well. And then we re-estimate each of the parameters for each of the refits or each of the parametric bootstrapping realizations, and then we sum the results, and that provides us with an empirical distribution of the values. So for instance, in the subepidemic wave model, which is a 5-parameter model, we would use the least square fitting of the model solution to the observed incidence data. We would model the confidence intervals for the parameters, and we would also use get the 95% prediction intervals of the model fits using this parametric bootstrapping approach. And the time series of the case incidence data is an aggregation of all of these. Looking at the figure, the lower figure, we can observe that their model fits, which is the blue lines, is given by the F, Ti, and Phi. And the parameter uncertainty is derived from simulation of the study by using is derived from our simulation study, and the blue circles here denote the actual data. These are some of the fits from the GGM and the GLM models. And like I said, that the generalized growth model usually fits best the early phase of the epidemic. And we're fitting here the Chile and the Peru data. So fitting the first 25 days of the Chile data and fitting the first 17 days of the Peru data, we observed that the model fits well. And these are just very simple models, the 2-parameter GGM model. And we can observe that the parameters, which is the R growth rate and the P parameter, are very well identified, and we can observe the sub-exponential growth dynamics. However, fitting the generalized logistic model to the Lima Peru data doesn't really give us very well identified parameter estimates, and the reason being that K, or the final epidemic size, is more identifiable or well identified when the epidemic has already reached its peak or is about to reach the saturation point. So if you observe in Chile figure on the right-hand side, the bottom right-hand side, you can see that the parameter K is much well identified. The reason being that we have almost reached that peak or the saturation point here. So similar to how we perform the parametric bootstrapping approach for fitting the data to the model to the data, we would do it also for performing the forecast, where we would generate multiple bootstrapping approach from the different model fits to get the forecasting period, the mean of the forecasting period, and also the 95% prediction intervals around the data. And then we can compare how the data in the forecasting period or the forecasting horizon matches with the forecast that we produced. And to basically assess the performance of the forecast, we use 4 major metrics, which is the mean absolute error, the mean squared error, the mean interval score, and the 95% prediction interval coverage. And recently, we also sometimes use the weighted interval score. So the mean absolute error basically is the distance between the model fit and the data. The mean squared error is basically the square of the difference between the model fit and the data. The mean interval score and the prediction interval coverage account for the uncertainty of the prediction. So the mean interval score addresses the width of the prediction interval coverage and also the coverage. And it basically employs the information about the uncertainty of the model fit. So in these equations, you can observe we have YTI, which is the actual time series data, which could be the incidence or the death data. Then we have the FT, TFI theta, which is basically the model fit, and then the U sub TFI, and then L sub TFI is basically the upper and the lower 95% prediction interval coverages, and the factor I, or the variable I, is the indicator variable. So moving forward, I will show you some of the examples of the COVID-19 model fits and the forecasts that we have performed for different countries and how our models performed during these different parts of the pandemic. So the COVID-19 pandemic in Mexico, for that, we fit the data to the depth data, and we retrieved the data from the IHME model, the Institute of Health Metrics and Evaluation. And if you can observe that in Mexico, we observed kind of like a bimodal pattern in the number of deaths. And while we fit our models to the data, to the cumulative mortality forecasts in Mexico, as you can see in the figure, for the sub-epidemic wave model, we're pretty close to the cumulative mortality forecast that we obtained from the IHME models. And we used 3 different scenarios for the IHME models, which were the mandates easing, the face masking, and then where there was the bad performance of the where you would remove the mask, basically, or no mask. So as you can observe, from the x-axis, we are comparing the cumulative forecast for the GLM model, sub-epidemic wave model, Richards, and the 3 IHME scenarios. And if you can see, the mean of the sub-epidemic wave model is much closer to the mean of the IHME models, and the actual horizontal line, which is the actual mean of the cumulative forecast that was obtained in real time. This is the actual reported cumulative mortality data from Mexico, basically. So even in Mexico City, we can observe that the sub-epidemic wave model did much better compared to the other 2 models, which is the Richards and the GLM. And for the Richards, you can observe that we have much wider 95% confidence intervals compared to the other models. So Moving forward, I'll show you how our forecast with the GLM Richardson subepidemic wave model differed or showed compared to what the actual data was like. So if you can observe in these figures, the blue dots are the actual data, the red dashed lines are the 95% prediction intervals, and the red solid line is the best model fit. And if you can observe, these were the sequential mortality forecasts that we did from Mexico, starting back in March and ending around in the end of October. And as you can observe, the GLM model always predicts a downward trend in the number of deaths. However, the horizontal dashed line is basically the line that separates the calibration period from the forecasting period. So you can observe that in the forecasting period, the incidence data is not declining, not at least in the last 6 forecast periods, but the GLM model nonetheless is showing a declining phase. Similarly, for the Richards model, again, it shows all through a declining trend in the number of deaths. However, for the number of deaths that were reported during that time period, we can easily see that they are not declining. Interestingly, the subepidemic wave model was able to reproduce the stability or the plateau in the number of deaths that the GLM and the Richards growth model was unable to reproduce. So you can observe, at least in the last 3 forecast periods, how our model really fits well with what the forecasting data looks like. So our forecasts were pretty much on point for the last 3 forecast periods. And even early on, our model is not really depicting all the way the downward trend, but it's showing some plateau in the region. And again, for the Mexico City, again, our model was able to reproduce that stability of the plateau in the forecasting period compared to the other models, where we can observe that the deaths data is within the 95% prediction interval coverage for the forecasting period. In terms of the performance metrics for Mexico, and here I would like to emphasize that we have the blue dots, which depict the subepidemic wave model, the magenta depict the GLM, and the red depict the Richards growth model. So higher the 95% prediction interval coverage, better the performance, lower the root mean square error, mean absolute error, and the mean interval score, better the performance. So as you can observe, the subepidemic wave model does much better than all of the other 3 models in terms of all the performance metrics, where we have lower values for subepidemic wave model in terms of RMSE, mean absolute error, and the mean interval score, and higher values for 95% prediction interval coverage. And similarly for Mexico City, again, we observed that our subepidemic wave model does much better than the Richards and the GLM model. Again, the blue dots showing the subepidemic wave model, the magenta showing the GLM, and the red dots showing the Richards growth model. Another example is our recent work with the COVID-19 pandemic in Colombia. And as you can observe, we can observe a 3-modal pattern of the COVID-19 pandemic in Colombia. And with the most recent upsurge, we observed that our GLM model, and for Colombia, when we performed the forecast, we used all of the departments in Colombia. So we performed national level forecasts, and then we divided the departments into the 5 regions, which are the Amazon, Caribbean, Indian, Pacific, and the Orinoco region. And as you can observe, that our GLM model depicts a stability in the forecast period during the Amazon region, and an incline for the Pacific and the Orinoco region. I would like to emphasize here, though, that the data after the vertical line is the forecasting data, is the data that we're comparing our performance with. But this last 30-day data, so these are 30-day ahead forecasts. The last 30-day data, however, can be a little non-accurate because of the reporting delays or some of the cases that have not been reported yet. So hence we see this major decline in this in the data points. Again, the Richards model shows a decline no matter what in the forecasting period. And very interestingly, if you observe, we see that the Richards model is unable to fit the early data really nicely. And why is it unable to fit is because it lacks the P parameter, which fits the sub-exponential pattern, or which fits the sub-exponential growth. And when we looked at different values of P across different regions and at the national level for Colombia, we did observe sub-exponential growth pattern across the board for the COVID-19 pandemic. And the subepidemic wave model, as you can observe here, exhibits an upward incline in the forecasting for the national region, and for the Amazon, it is a stable, and even for the Caribbean, it kind of takes that plateau region. But for Caribbean, we do see the upper bound of the 95% prediction interval goes up, which means that the cases might just go up again. And then we have the Pacific and the Orinoco region where it shows a decline. And all of these forecasts were done between June 1 and June 30. So these are 30-day ahead forecasts. Another example for the COVID-19 pandemic in the United States of America, where we are seeing another upsurge in the cases because of the Delta variant and the number of people that are unvaccinated, we perform every week, we perform the COVID-19 forecast using the data from Johns Hopkins webpage, and we fit the models to the last 90 days of the data by calibrating our models to the last 90 days, and we perform a 20-day ahead forecast to see what the next 20 days might look like. And we publish these forecasts, the real-time forecasts, on this webpage that you can observe. I have the link to that in the slide. And it looks like this, and this is the most recent forecast that we performed for July 27th. We'll be performing a forecast every Tuesday, and then when we publish it every Tuesday, so you can go ahead and check the webpage out and see how our forecasts have evolved over time. And these are the ensemble forecasts where we're trying to get to the best possible forecast using the different ensemble models. So a little bit about different time periods and how our models were able to capture the actual data in the forecast period. So this is for the summer resurgence in the United States of America. And you can see that we have 4 different models for this. And we can observe that for the first, third, and the fourth model, the models did not really capture well the data in the forecasting period. As you can observe, the red circles, which is the data in the forecasting period, and the any part of the model fit, and the 95% prediction interval after the horizontal line is the forecasting horizon. So these models have not been really able to capture well the actual forecasting data. And if we observe the subepidemic wave profiles for all of these 4 models, we observe that the gray one here is the active curve. The red one is the first subepidemic, and the blue is the second subepidemic. And we can observe that all of these models show that there's 2 subepidemics, and the second subepidemic is taking off as the first one's declining, right? And all of these are showing kind of like an upsurge or an increase in the trajectory of the epidemic. However, our ensemble models for the summer resurgence in the United States of America did perform well in capturing the actual data in the forecasting horizon. And as you can observe, we have a much wider 95% prediction interval in the forecasting horizon, which means that there's greater uncertainty here as well. So for the fall resurgence, again, as you can observe, our first, third, and fourth ranked models do not perform really well with the capturing the actual data during the forecast period. The second ranked model did do better because it had a wider 95% prediction interval coverage. And as the subepidemic wave profiles can be seen and observed, that each of the subepidemic, as the first subepidemic, the red one declines, is declining, the blue curve is starting to show up, which means that there is another subepidemic that's taking off, and the coarser grayscale subepidemic is an aggregation of both the red and the blue curves. However, our ensemble model for the fall resurgences did a much, much better job at capturing the data in the forecasting horizon. And as we can observe, the 95% prediction interval coverage is also much wider here compared to just our simpler models. For the spring 2021, we have, again, the 4 models, and these are ranked based off of the AIC, or the AIC information criterion. And we can observe that these models have done much better at capturing the data in the forecasting horizon. And the ensemble models also do a pretty good job at capturing the data during the forecasting horizon. And looking at these calibration performance statistics, which means the performance metrics during the calibration period for the 90 days that we fit the models to the data, we can observe that the mean absolute error, the 95% prediction interval coverage, and the weighted interval score, which is basically a performance metric to measure the interval score format, are pretty similar to each other. So we don't observe much difference between the performance metrics for the best models or the ensemble 2, 3, and 4 that we observed previously in the slides. And even for the mean squared error, the 3 ensembles do pretty evenly compared to the best model fit. And for the forecasting performance, we observe, that our ensemble 4 does better at the mean squared error and with the mean squared error and the mean absolute error compared to the best model fit, which is selected from the 4 models, the 4 ranked models. And for the weighted interval score, again, the ensemble 4 model does much better compared to the other 2 ensembles or the best model fit. And the last example that I will present, last 2 examples are from China. So the COVID-19 pandemic in Anhui, China showed this kind of a epidemic curve where there was an increase in the resurgence right at the beginning when the pandemic started in that region. And this is, just to be clear, a 7-day average curve. So when we fit our 3 models and the ensembles 1 and 2, we can observe that our model fits for the ensemble models during the calibration period and even the forecasting period did much better compared to our 3 models, the other 3 models. So in model 1, we can observe that our the upper bound is pretty high or is pretty distant from the lower bound or the model fit for the first 2 periods. And then for the model 3, it has a much better fit. And then these models show a decline in the number of cases, which was the case with the actual data in that time period. And the performance metrics, as can also be observed, the mean absolute error, and here we're basically comparing the Gompertz, Richards growth model, the generalized logistic, and ensemble 1 and 2, as we can see here with these, the model 1, 2, 3, and then ensemble 1 and 2. So we can observe that for the 95% prediction interval coverage, our ensemble model 2 does much better compared to any of the other models. And then on the second, we see that the GLM model has the greater 95% prediction interval coverage. However, in terms of the mean absolute error, we observe that the Gompertz model and the ensemble 2 model do pretty equal. And then for the mean, which means that they do better than the other models. And then for the mean squared error, again, we observe the Gompertz model does the best compared to the ensemble model 2. And then for the mean interval score, again, the ensemble model 2 does better than any other model. So like I said earlier, lower the mean absolute error, mean squared error, and mean interval score, better the performance. And then higher the 95% prediction interval coverage, better the performance. And then lastly, for Hunan, China, again, the curve showed an increase right when the pandemic started. So there was an uptick in the number of cases, which then declined. And then we did not really see any more cases. And then again, fitting the GLM, Richards, and the Gompertz model, and then comparing them with the ensemble model 1 and 2 using the subepidemic wave model, we observed that, again, the GLM is not really a good, it does not really predict well the forecasting during the forecasting horizon, the number of cases that we would be observing. However, the Richards model and the Gompertz, the Richards and the Gompertz model do much better. And very evidently, the ensemble models have been doing really better. And ensemble model 2 does really good job at capturing the data during the forecasting period. As you can observe, the blue circles, which is the data in the forecasting period, is inside of the black dashed lines, which is the upper bound of the 95% prediction interval during the forecasting period. So looking at the performance metrics for this Hunan, China, we can observe that again, for the mean absolute error, the Gompertz still does better, for the mean squared error as well, and for the mean interval score, the ensemble 2 does better, and also for the 95% prediction interval coverage, the ensemble 2 does better. So looking at all of these models and comparing them across time, we've been able to figure out what model does better at what with what data at what period in time. And clearly the ensemble models that we have been working on using the subepidemic wave model, which utilizes the generalized logistic growth model as a building block, has been really helpful in understanding the data during the calibration and forecasting period. And our forecasts have been doing decent enough during the most recent time periods. So in summary, we can see that the mathematical models provide a framework to quantify the transmission of the infectious diseases. The forecasts obtained from these models can assess the potential scope of the pandemic in real time. They can provide insights on the contribution of disease transmission pathways, predict the impact of control interventions, and evaluate optimal resource allocation processes to inform public health policies. We have seen that the subepidemic wave model has shown competitive performance in the 30 and 20-day ahead forecasts, and the subepidemic modeling framework exhibits good calibration properties for the COVID-19 pandemic in the USA that I showed you in the previous slides. And the ensembles of the best subepidemic models substantially increased short-term forecasting performances. So the 95% prediction interval coverage from 43% with the best models to 63% with the ensemble model of the top 4 models. So as we move from the top ranked models to the ensemble models, we get a greater coverage of the 95% prediction interval coverage. And also we observe a substantial decline in the mean squared error, mean absolute error in the weighted interval score, which means that our models are doing much better. And then we have also been comparing our forecasts with some of the forecasts that are present with the COVID-19, with other COVID-19 forecasters using the CDC Forecasting Hub. I would like to really thank my mentor and my advisor, Dr. Gerardo Chowell, that I've been working with. It has been an honor to be working with him, and I've learned so much during this time period of my PhD. Also, my Second Century Initiative Fellowship that I've been awarded with from the Georgia State University to fund my PhD. My lab mates, Dr. Kimberly Ruza, Sushma Dhal, and Yisuli, and then some of the collaborators that we've been working with from Mexico, Colombia, United States, and other countries. And then these are some of the references for the papers that we've been working on and that we've used in this. And then for any questions, I'd be happy to take any questions now, or if you want to email me. So thank you very much.
Okay, thank you for your interesting talk. We had a question from
Yes.
the audience.
Yes, please.
From Professor Manik Nava from Sciences School, National University of Mexico. It's been shown that classic no-spatial epidemic model size SIR overestimates the transmission rates as opposed to spatial models. How could one discriminate between slower transmissions due to important spatial phenomena and due to the underlying substructure in the outbreak weights? And do you consider it could be helpful to extend your model to consider space, or would it become unnecessarily complex? The question is in your chat from the Zoom chat.
Oh, it's in the chat. Sorry. Thank you. Oh, I'm looking at it now. So thank you for the questions. I would like to mention that using the phenomenological models are simpler models, and these do not incorporate the different parameters such as the latent period, transmission rates, or infectious period. We do not incorporate these in these models. So you are correct that the SIR models do overestimate the transmission rates compared to the spatial models. But these phenomenological models that we're using to forecast the epidemic trajectories do not incorporate or show any of the transmission rates how the transmission rates differ. And then you are correct that including the spatial or the space in the model could be an interesting thing to look at, that we can definitely look into, but we have not yet incorporated that piece into the model.
Thank you. Okay, Gilmer, do we have another question?
No.
Okay. Very interesting talk. We are working to describe epidemics with several peaks using SRIR model.
Okay.
But considering the infection rate as a function of time,
Okay.
we have obtained very good results. It's
Excellent.
another
I would really-
direction of your work. We try to replicate several peaks.
Yeah.
But another direction.
Yeah.
You from a statistics point of view, and we from ordinary differential equations.
Yeah.
Okay, very interesting talk.
Thank you very much.
Your talk will be posted in the channel of the webpage for your diffusion of as part of the activities this event.
Okay. Thank you very much for inviting me.
You can follow your rating of visiting to talk.
Okay. Thank you very much.
Thank you very much. Please say hello to Gerardo for me.
I will. Thank you.
Thank you very much.
Thank you so much. Have a good day.
It was a pleasure to know you.
Yes, same here. And I'll definitely look into your papers that you're using the SIR models to fit the multiple peaks. That'd be really interesting. I'll definitely take a look at your work.
Okay.
Thank you very much. Have a good one.
Thank you very much.
Bye.
Bye.